Very good. So good morning again, everyone. Uh, it's my pleasure to welcome you back to another of these RHIC-BES seminar series. So I'll go ahead and introduce our speaker today, and then our chair will take over in a little bit. So it's my pleasure today to introduce Xiaojun Yao. He's going to talk to us about classical and quantum computing of shear viscosity for 2+1D SU2 gauge theory. And I understand that Xiaojun was a student at Duke University with Bert Mueller, who very many of us in the field know. And so we're very much looking forward to hearing about this topic. So I'll turn it over to you, Xiaojun. Thank you.
Thank you very much, Daniel. And I also would like to thank the organizing committee to giving me this chance to talk here. And today I will talk about the recent work that I did with Francesco Turro, Anthony Ciavarella, which is to use quantum computers to calculate shear viscosity. And I will use the 2+1D SU2 pure gauge theory as an example to illustrate the algorithm. Let me start with the introduction about heavy ion collisions, quark-gluon plasma, hydrodynamics, and shear viscosity. For the experts in the audience, please bear with me for a few slides. And we all know that we collide heavy nuclei in the laboratory. We accelerate them to the relativistic speed and let them smash in the laboratory. And in the laboratory, right after the collisions, there are many particles of matter produced. And the temperature reached in the central of the collision is so high that the quarks and gluons becomes deconfined. And we call this deconfined phase of nuclear matter the quark-gluon plasma. And this plot is the phase diagram of nuclear matter. The y-axis is the temperature, the x-axis is the baryon density. And at a sufficiently high temperature, we enter this deconfined phase called the quark-gluon plasma. And these are current experiments studying the properties of the quark-gluon plasma. They're running at LHC. They're also running at RHIC. And these are the regions in the phase diagram these experiments can probe at the moment. And particularly, the RHIC program is trying to search for the critical point in the phase diagram of QCD matter. In the heavy ion collisions, we can have both central or peripheral collisions. In the central collisions, the two nuclei just have a head-on collisions. But more often, we will have peripheral collisions where in the transverse plane, the two nuclei are overlapping partially. And there are some regions they just pass through each other. And due to this essential eccentricity, the particles moving along the kind of x-axis in this plot have a larger momentum than particles moving along the y-axis. And this initial eccentricity is translated into an isotropy in the final particle distribution in the azimuthal plane. And we measure this distribution in the transverse plane and analyze them in terms of harmonics. And we call this distribution the collective flow of particles. And for example, when n is 2 here, we have a cosine 2 phi. And that coefficient is called elliptic flow. And for n equals 3, that is called a triangular flow. And in this plot is an example of measurements by the Lattice collaboration, where they have measured V2, V3, V4 for both the 2.76 TeV and 5 TeV collisions. And as you can see from these plots, in central collisions, the signal is much smaller than that in peripheral collisions. And the experiments can measure these collective flow coefficients to very precise precision. And in our field, we have been kind of using hydrodynamics to describe collective behaviors for a long time. Hydrodynamics is an effective theory describing the energy momentum conservation, and it's a long wavelength effective theory, and it's based on expansion called the gradient expansion, which is based on the long wavelengths. And if we expand and keep terms up to first order in terms of derivatives, and we arrive at this expression for the stress engine tensor. So for the leading term, we have the energy density plus the pressure times the fluid velocity, and minus the pressure times the metric of the system. And this is a linear order correction term. Here, for simplicity, I drop the bulk viscosity term and just keep the shear viscosity term. So eta here is called shear viscosity, and this term is an antisymmetric traceless part, depend on the first derivative of the fluid velocity. And this is called the Navier-Stokes hydrodynamics. But to make it causal and in practical calculations, we will use the Israel-Stewart formulation of the hydrodynamics by adding some relaxation terms such that the whole theory is causal. But I won't go to the details here. And let me just give you a kind of everyday experience of how shear viscosity works. Let's think about a fluid. It has two boundaries. The lower boundary is fixed, it's static there, and the top boundary is moving at some constant velocity. And due to shear viscosity, different layers of this fluid will exert force onto each other. So the top layers will exert force on the lower layers such that the lower layers will move at a relatively smaller velocity, but in the same direction as the top layer. And the force between different layers of this fluid is proportional to the area between the layers and also their velocity gradient. But this proportional constant is called shear viscosity. And for our kind of daily life experience, if you think about some fluid or liquid like water or honey, if you try to stir the water or honey, you will feel a different resisting force. And that force is coming from shear viscosity. So in quark-gluon plasma, in heavy ion collisions, we try to quantify the property of the quark-gluon plasma using its shear viscosity. And we have been using hydrodynamics to confront with experimental data and try to infer the value of shear viscosity. So in this plot, it's an early study of the V2 coefficient as a function of the charged particles produced. And we have the data collected from the RHIC experiments. And this is a simple hydrodynamic calculation with some simple initial conditions called the Glauber model, and some simple hydrodynamization models and the URQMD for the hydronic phase. As you can see from this plot, by using the shear viscosity over entropy density as 0.08, we can describe the data well. Using other values like 0 or 0.16, we miss the data a lot. And this comparison indicates that the shear viscosity extracted from the heavy ion collision data is very small. That means the quark-gluon plasma produced is almost a perfect fluid. And since this early work, there has been many studies using modern techniques to try to do a more kind of accurate extraction of the shear viscosity. And this is one of the most recent studies where they also include the uncertainty band of the shear viscosity over entropy density as a function of temperature here. So the blue band here is the uncertainty, and they also have a temperature dependence here. But quite interestingly, within the uncertainty of this extraction, the value of the shear viscosity over entropy density at a low temperature is very consistent with 1/4 pi, which is calculated holographically for strongly coupled supersymmetric Young-Mills theory. And this analysis also analyze different observables like V2, V4, and using different correlation methods. Okay, so I hope I have persuaded you shear viscosity is very interesting in our field, but calculating shear viscosity in QCD is very challenging. Back in the days, people started using perturbation theory to calculate these real-time observables. And I have to say, these studies started at the University of Washington by a group of people. They are the pioneers who use perturbation theories to calculate the shear viscosity. But over the years, we found the perturbation theories is very difficult to control to give a reasonable results for the shear viscosity. For example, this is a recent study at next to leading order accuracy. They calculate the shear viscosity over entropy density as a function of temperature. So there are two things I want to draw your attention to this plot. First, at very high temperatures, say when temperature is equals 1 TeV, at which we believe perturbation theory is applicable, if you look at the difference between leading order and next to leading order difference, they differ a lot. And that may indicate, the perturbation theory may not converge well, even though we believe this scale is good for perturbation theory. And then on the other hand, at very low temperatures where we believe perturbation theory would fail, we see a large uncertainty band caused by the scale fixing procedure in the perturbation theory calculation. And this again indicates that the perturbation theories may not be applicable at such a low temperature. But we also have non-perturbative computing methods, such as Euclidean lattice QCD approach, which is based on path integral and numerically sample the important configurations using statistical techniques. And in the Euclidean lattice approach, we analytically continue the two-point function for the stress engine tensor to the imaginary time. And by evaluating this g tau function on the lattice, we can try to reconstruct the spectral function of the system. And the spectral function rho is defined in this way as an integral equation to connect it with the g tau measured in lattice QCD calculations. And the kernel of this integral, k, is a standard expression that involves the time of the imaginary time on the lattice, the temperature, and also the frequency at which we evaluate the spectral function. And the shear viscosity can be extracted from this limit of the spectral function. Mathematically, this looks kind of a well-defined procedure, but in practice, it has a lot of problems because we only know a finite number of points of this g tau, but we want to extract a continuous function out of this integral function. This is an ill-defined inverse process. In fact, if we use different spectral functions, we can get the same g tau. And furthermore, if we look at this kernel function at small frequency, this function is very insensitive to the tau. And that means if we want to use measurements at several tau on the lattice and try to infer the information at omega close to 0, that is almost impossible because the kernel is insensitive to the structure of omega when omega is small. And that means we only know the integral of this rho omega over omega when omega is small. We could not be able to infer the structure of the rho omega when omega is small. Okay, that's the current status of calculating shear viscosity in QCD. And I hope I have to motivate my talk enough. And here is the agenda of my talk. So I will discuss calculating shear viscosities using a different formalism, which is based on the Hamiltonian approach. And we will use the Hamiltonian lattice theory, which would allow us to calculate real-time observables. We don't need to go through the ill-defined inversion process. We can extract the shear viscosity directly from the real-time correlation function. And in the talk, I will show you the calculation setup, and then I will show you as an example the 2+1D SU2 pure gauge theory. And then I'll show you some classical computing results on a small lattice with highly truncated local Hilbert space. And then I will show you the quantum algorithm to calculate the shear viscosity. Okay, so let me start with the real-time formalism. So the idea is to use the real-time Kubo-formula to connect some real-time correlation functions and the shear viscosity. So this is the Kubo-formula. On the left-hand side, we have the non-equilibrium transport coefficient, the shear viscosity. On the other hand, we have a real-time retarded Green's function evaluated at the thermal equilibrium. So let me explain the definition of the correlation function here. So this correlation function is written in the frequency space, but we can do a Fourier transform and then go back to the space-time space. And we integrate over the position. Since we're looking at a 2+1D theory, we have two spatial dimensions here. And this retarded Green's function is defined in this way. We have a commutator of two stress engine tensors, the Txy, at the different times and the position, and evaluate this trace of the commutator at a thermal equilibrium. So this rho T here represents the thermal density matrix at a finite temperature given by 1 over beta. And the Txy from our field theory textbook can be written in terms of the F mu nu for pure gauge theory. And for the retarded Green's function, we also insert a theta function here. So this is the definition of the retarded Green's function. And we can get the shear viscosity from this limit. But I want to emphasize this expression here is kind of a tree-level equation or tree-level matching condition. Because on the right-hand side, we can calculate this in the full theory. So there is no effective theory involved. But to really connect it to shear viscosity, we need to use the hydrodynamic effective theory, which is the effective theory. So it will have a cutoff. And in principle, these transport coefficients are Wilsonian coefficients of the effective theory, and their calculation depends on the cutoff of the calculation. But here, for simplicity, we just use this tree-level matching condition such that this eta does not have any scale dependence. But if we include higher order terms in the stress engine tensor expansion, eta will generate some scale dependence. But that's not the complication we're pursuing here. Okay, and then let's think about what happens if we know all the eigenvalues and the eigenenergies of the system. And by that, I mean we have a Hamiltonian describing the theory, and we diagonalize it to have all the eigenvalues En and all the eigenstates labeled by N here. The N corresponds to the energy E sub N here. And after some algebra, we can show the shear viscosity can be rewritten in this way. So we will take an infinite time limit of some integral. And in the integral, which I called eta tilde, we integrate from 0 time to a large time TF. And the integrand is just T, this T coming from the partial derivative with respect to the frequency. And also the imaginary part of the retarded Green's function. And if we know all the eigenstates and eigenenergies, we can insert a complete set of states into the trace involved in the definition of the retarded Green's function. And then we have this phase factor from the thermal density matrix. And then we have some matrix element between the stress engine tensor Txy and the two different eigenstates N and M. And we also have a kind of real-time factor here, this F factor. It's written in terms of the sine and cosine functions involving the energy difference between these two eigenstates and also the final time TF here. And in this expression, I have used the translational invariance of the system such that I inserted the kind of integrated version of the Txy. So it's not the Txy at a single position point, it's the Txy integrated over the whole spatial region. Okay, so this is the formula we're going to use to extract the shear viscosity in these real-time calculations. And let me now introduce the Hamiltonians that we will do these calculations. So example we are going to use is 2+1D SU2 pure gauge theory. And the Hamiltonian we're going to use is called Kogut-Susskind Hamiltonian. It's derived from the Lagrangian of the theory by working in the temporal axial gauge. And then we discretize the theory on a spatial lattice. So I want to emphasize the time in this formalism is not discretized as in the standard Euclidean path integral approach. On the spatial lattice, the Kubo-Susskind Hamiltonian can be written this way. So we have electric energy part and a magnetic energy part. So the electric energy part is proportional to J squared here. And the electric fields live on the links of the square lattice. So on the square lattice, we have links connecting the adjacent vertices. So the electric fields live on the links. And for the magnetic term, it can be written in terms of the plaquette term. So the plaquette is a purely spatial plaquette, like for example, a square winding around the smallest plaquette on the lattice. It's defined by the trace of 4 Wilson lines, and the 4 Wilson lines are in the fundamental representation of the theory, and they just wind around as shown by the arrows here. And the magnetic term is given by the sum of all the plaquette terms on the lattice. And this is just the lattice representation of the Wilson line. But we need to quantize the theory, which means we need to impose a commutation relation between these two observables, the electric field and the gauge link or the Wilson line. And this is a commutation relation satisfied by the electric field and the gauge link. So their commutation relation is given by this TA times the gauge link. This TA is the generator of the SU2 algebra. And this delta function here means the electric field only kind of have a non-trivial commutation relation with the gauge link living on the same link. If the electric field lives here and the gauge link lives here, then they don't have non-trivial commutation relation. And furthermore, the commutation relation of these electric fields satisfy this non-Abelian commutation relation. This FABC is just the structure constant of the representation of the SU2 group. So we know for SU2, this FABC is just the Levi-Civita tensor. And this commutation relation indicates that the theory is non-Abelian. So if I swap the order of apply this electric field, I have a non-vanishing result. And this means this group is non-Abelian. And if you can think of these two conditions as that the electric field generate a gauge transformation on the gauge links. Like the TA is just like how the group element transforms under the generator. And this just means the generators are non-Abelian. But since we're working in the temporal axial gauge, we have to impose the Gauss's law. And that means the physical states have to be a singlet when they are transformed at the vertex. And on this lattice theory, the Gauss law can be written as a summation over the electric field at the vertex and impose that when this operator acts on a physical state, a 0 is returned. And this is called the Gauss's law, and imposed at each vertex on the lattice. So let me explain that in a little bit more detail. So traditionally, we would use the kind of field basis to write down all the Hilbert space for this theory. But in fact, we can choose a different basis called the electric basis. And the electric bases are labeled by 3 quantum numbers, the J and ML and MR. So you can think of this J as just the standard angular momentum quantum number, like G equals 1/2 or G equals 1 for the spins of a particle. And the ML and MR are 2/3 components of this angular momentum J. And the reason why we need the 2/3 components is because the electric fields live on a link, and the link has 2 ends, a left end and a right end. And the electric field can generate both gauge transformations on the left side and also on the right side. And to characterize that, we need 2 quantum numbers, the ML and MR, to indicate how this link transform under a left gauge transformation and under a right gauge transformation. And as I said, this is a so-called electric basis. It means the electric field squared in this basis is diagonal. So when the electric field operator squared acts on this basis state, we just have J times J plus 1. This is just standard kind of angular momentum algebra. And as I said earlier, we will only work with gauge invariant states, which are physical. And to get the gauge invariant states, we need to impose the Gauss law at each vertex. And that means this state at this vertex would transform as a SU2 synclac state. And for example, if we have two links connecting a vertex, and the way we write down a SU2 synclac is just using the antisymmetric linear combination of these angular momentums. Like this, I hope this is familiar with the audience. This is just quantum mechanics, angular momentum addition. But with this antisymmetrization, this combination here would transform like a SU2 synclac. They would transform like a 0,0 state. But in practice, in this calculation, we have a vertex with 4 legs. So the kind of construction of SU2 synclac is more involved. And in fact, it actually requires extra overhead in the computation. So the problem is on the square lattice, we have 4 links joining the same vertex. And for simplicity, let's consider a plaquette where each vertex only have 3 links joining. And due to the properties of the SU2 group or SU2 algebra, if we specify the G values on the links that joined at this vertex, we can uniquely write down a SU2 synclac. So the SU2 algebra allows us to write down a unique synclac state if we know the G values on these 3 links. But that is not the story when we have 4 links. So if we know the G values on these 4 links, the SU2 synclac is not uniquely defined. We can define multiple SU2 synclacs if we know the 4 G values. So this in practice means we need additional labels to separate different SU2 synclacs. In principle, this can be done, but it's just a computational overhead, and we try to avoid it. And on 2+1D, we can avoid this problem by using a honeycomb lattice. So on the honeycomb lattice, each vertex only had 3 links joining, as on a plaquette chain. So this is a nice feature for computational simplicity, but it's not necessary. You can still use the square lattice and do some overhead tracking of the SU2 synclacs. But in this talk, we will work with the honeycomb lattice, and one can derive the discretize the lattice gauge theory for the SU2 theory. Again, it has the electric energy part, which depends on E square, and the electric fields live on all the links of this honeycomb lattice. And for the magnetic term, instead of plaquette, a square plaquette, now we have a honeycomb plaquette. It's defined by 6 gauge links or 6 Wilson lines in the fundamental representation. And since we have a honeycomb lattice, we just have some square root of 3 prefactors here, but they can be worked out systematically. Okay, so this is a lattice setup. We're going to discretize our theory and get all the eigenstates and eigenvalues. But as I said, we're going to use electric basis where the electric energy is diagonal, but we still need to work out how the plaquette would look like in this spaces. So let us focus on one plaquette on the lattice. So this plaquette has 6 vertices and the 6 external legs or links labeled by the dashed lines here. And for this vertex, I call the internal links A and B, and this dashed line X. This is the external link. And we want to work out the matrix element of the plaquette operator between 2 different basis states. Like the state is labeled by the G values on all the links in this diagram. And the initial state is labeled by small g, and the final state is labeled by capital G. And one can work out the matrix element is written in this way. It depends on the external G values and also depends on the internal G values. And it's a product of the 6 vertices of this honeycomb lattice. And this symbol here, this curly bracket, is the Wigner 6G symbol. It just encodes the Wigner, the Clebsch-Gordon coefficients of the theory in a nice way. So we can write it in a compact way, but in practice, it's expansion in terms of Clebsch-Gordon coefficients. Okay, so with these expressions, then we know the Hamiltonian's matrix element in this electric basis. we can diagonalize the Hamiltonian and find all the eigenstates and eigenvalues if the lattice is not big. But for our calculations of the shear viscosity, we also need the operator for the Txy, for the stress engine tensor. And in this case, the Txy can be written in terms of the electric field along the x and the y directions. But here by x and y, I mean the Cartesian coordinate. So x is a horizontal and the y is vertical. But since we are working with a honeycomb lattice, the electric fields have different orientations. For example, the E1 here is pointing along this direction. E2 is along the traditional negative y direction, and the E3 is along this direction. So we need to kind of work out this Ex, Ey in terms of the E1, E2, E3. And by the Gauss law, the summation of these three electric fields is equal to 0 when acting on a physical state. So we can use this property and rewrite the Ex, Ey in terms of the E1 squared and the E3 squared. So in this way, we can encode this Txy operator and write down its matrix element in our electric basis. And then we have everything to do the calculation. But in practice, since we are working with a finite lattice system, we need to do a truncation in the electric basis. So the highest value of the electric basis we're going to keep in the calculation is called Gmax. And first, let us study this Gmax cutoff effect on the theory. So here, I just consider a 2x2 honeycomb lattice with coupling G squared equals 1. And then I study the energy density and entropy density as a function of temperature on this small lattice, and I vary the cutoff in the electric basis. So first, let us look at this blue line here. This one has the lowest cutoff, which is 1/2 here. As you can see, this is the energy density as a function of temperature, and this is the entropy density as a function of temperature. And now we increase this Gmax cutoff. We see the energy density increases, same as the entropy density. But when the Gmax equals 2, we see little change here, say below 5. When the temperature is below 5, we see kind of a convergence for the Gmax on this small lattice. But in this same plot, I also plot a dashed line, which is kind of a naive expectation from the continuum theory. For example, in a free continuum theory, we'd expect the energy density grows like T cube. But in this plot, you can see on this small lattice, we can only achieve the T cube in this region here. At the sufficiently high temperature, we are deviating from the T cube dependence. And that means we need to enlarge the lattice and using larger Gmax cutoff to reach the continuum behavior. And a similar story applies to the entropy density. So from a free continuum theory, we'd expect this entropy density grows as T squared, but we only achieve that when the temperature is small. At sufficient high temperature, the lattice is too small to contain a kind of a low wavelength mode, and also the Gmax cutoff is not large enough. Okay, and analytically, we can write down a good estimate of the Gmax we need. For example, if we want to describe all the states up to an energy given by E with an error given by epsilon, the minimum Gmax we need is, the maximum Gmax we need can be estimated in this way. Is given by the number of links on the lattice and the energy of the states we want to keep track. And this energy E tilde is given by the energy of the states plus the kind of a constant term that depends on the number of plaquettes. So the numerator here depends on the volume or depends on the area of the lattice. And the numerator depends on the coupling and also the accuracy that we want to describe the system. So as you can see from this expression, in practical physical calculations, we need a large Gmax. Okay, but I mean, the large Gmax would require an exponential large amount of resource, and we don't have that yet, at least classically. So we want to seek some simplifications, and one great simplification happens when we work with the lowest cutoff, when Gmax is 1/2. And in this limit, the theory can be written in a nice way as a spin system where the Hamiltonian can be written completely in terms of Pauli matrices. So let me explain how this simplification works. So let us start with a strongly coupled vacuum where every link here is in the kind of lowest state when J is 0. So it does not carry any electric energy, no electric flux in the lattice. But now if we apply a plaquette term, a magnetic term from the Hamiltonian, let's say we excite this plaquette to J equals 1/2, labeled by this blue solid line here. So this plaquette is now excited. But if we think in terms of the spin language, our initial state is just like 5 spins pointing down because they are not excited. But when we apply a plaquette on this 0, 0 side, we actually excite this state to spin up. And that corresponds to a sigma x operation here. If we apply another plaquette term on the same at the same location, then we will go back to this state because we truncate at G equals 1/2. In principle, we could have a state with G equals 1, but that one is truncated off. So we go back to this dashed line case. And that is, again, like a sigma x operation applying to this spin up, and then it becomes a spin down. And then if we apply another plaquette operator on this 0, 1 location here, we get this state here. But the link shared by these two plaquettes go back to 1 because we truncate at G max equals 1/2. In principle, this link can become G equals 1, but since we
Let's see, do others still hear me?
Yes.
I don't think I can. Oh, okay. So it's not just me. Okay.
Yeah, I thought I was disconnecting. Seems.
No, we lost the speaker, I guess.
Yeah, it looks like it. Okay, apologies. Let me try to get a hold of him, make sure he understands that he got disconnected. And hopefully we'll be back in just a moment. Okay, he's going to try to reconnect. Hopefully it just takes a minute.
Oh. Hi, sorry, I think I dropped out somehow the internet connection. Can you hear me?
Yes, glad you were able to connect back.
Okay. Can you tell me when I dropped out?
Yes, go back to your slides.
Yeah.
Go. So it was on 15, I believe.
15. Okay. Okay, good, good.
Great. Glad you could come back in. So please go ahead.
Sure. Thank you. Yeah, sorry, there's some internet connection problem. Yeah, so on this slide, I just try to explain how we map this theory onto a polymatrix spin theory using this kind of mapping. And in the end, we just have a simple Hamiltonian that can be written in terms of polymatrices acting on spins. And this represents the original theory when the G max is cut at 1/2. Okay, so here are some results on the small lattice with this G max equals 1/2 cutoff. And here we fix the coupling and also the temperature to be 0.3 in terms of the lattice units. And we just plot this eta tilde as a function of TF for a 3x3 honeycomb lattice and a 4x4 lattice. And you can see the 3x3 lattice, the results are fluctuating largely here. And this fluctuation in real time is caused by the finite number of eigenstates we have in the system. So we have the eigenstates, and on the finite lattice, they are gapped. At late time, we start to probe the gap between neighboring eigenstates, and that is why we see the large fluctuations here. And that is mainly because we have a small number of states. And the situation becomes better when we have a bigger lattice where we have more states. The spectrum becomes denser such that the oscillation becomes smaller. As you can imagine, if we have a much bigger lattice or much more states, we will have a continuum or a smooth curve in the end. But right now we just work with a finite lattice. So this is all these fluctuations are finite lattice artifacts. But we still want to extract some physical observables out of this. And what we do is we fit this fluctuating function by some smooth curve, like decaying exponentially. And we try to extract this plateau value. And this plateau value is what we call the shear viscosity. And you can see, the signal is fluctuating, but since they're fluctuating up and down, the central values can be somehow fixed with good accuracy, numerical accuracy. But there are systematics built in this extraction, and we are still far from pin down that systematic uncertainty. Okay, that is a result at the fixed coupling, but for gauge theory, for lattice gauge theory, we need to take the continuum limit, and by that, we need to tune the coupling in such a way that we are approaching the continuum limit. And for the SU2 in 2+1D, the running coupling has been worked out by our chair, Prof, and the formula is written this way. So basically the coupling G square is a constant, and the AG square is running with A in a linear way. And what we did in this plot is we just calculate the eta over S at the several couplings AG square, and they're labeled by the black points. And then we try to extrapolate towards zero coupling here. And we use several functions, and we use several ranges of the data for this extrapolation and try to get a sense of the numerical uncertainty in this procedure. And so far, what we get is kind of roughly on the order of 0.1 at the moment with some uncertainties here. And the uncertainty is large here because the fitting function has an exponential that grows at a large coupling, and that is reflected in this large band here. But I want to emphasize that right now we're only work with a lattice model with a large Hilbert space truncation. We are not taking the real kind of physical limit yet. And in these uncertainty estimates, we only include the numerical or statistical uncertainties. there are unspecified systematic uncertainties associated with this extraction at the moment. And furthermore, we can repeat this exercise on this 4x4 lattice with a large truncation and try to get this kind of zero coupling eta over S at several temperatures. And you can see from this plot, at small temperatures, we have a large uncertainty due to the oscillations of the kind of eta tilde I defined earlier. And also we get a kind of a wrong temperature dependence because you would expect the shear viscosity will grow at higher temperatures, but we see the opposite. And that is a kind of another lattice artifact of this Gmax truncation here. And we also look at the spectral function in these model calculations. And the spectral function can be evaluated in this way if we know all the eigenstates and the eigenvalues. So we just take the difference of the En and the Em separated by a small omega. And these exponential factors here can be approximated in this way. So this spectral function will depend on omega in a linear way here, but it also depends on it through this matrix element. And in this plot, we just plot this matrix element magnitude, and we see a peak structure here. When the omega is small, which means Em minus En is small, we see a peak structure here. And let's also compare with known results. For example, for perturbation theory, we know there's a peak structure here, but for EDS-CFT calculations, we know it's a plateau there. But in our model calculations, we see a signal of peak structure there. But in the futures, we should investigate whether this peak stays in the continuum limit. Okay, so I finished the first part of my talk, and let me just give you a brief recap, and then I'll move on to quantum computing. So the key idea is to use the Hamiltonian formulation to do real-time calculations. It will allow us to calculate the retarded Green's function and extract the shear viscosity. But we need to take the physical limit, which means we take the lattice spacing going to 0, which means the coupling is going to 0. And that in practice would require take the cutoff of electric basis to infinity. We also need to take an infinite volume limit, the lattice size going to infinity. And we also need to take into account necessary operator renormalization because the lattice breaks the Lorentz symmetry and the T mu nu is no longer a conserved operator. But the three can be worked out sort of analytically, but 1 and 2 have to be done numerically, and they are very challenging in practice. For example, for the results I just showed you on a 4x4 lattice with Gmax equals 1/2, we already have 65,000 states. If we want to work with a 3x3 lattice with Gmax equals 1, we would have more than 500,000 states. And classically, if we want to do an exact diagonalization of such a large Hilbert space, that cannot be done because we don't have enough memory or space to store all the eigenstates. So exact diagonalization in classical computing cannot take us far. And that's where we start to resort other computing methods, for example, quantum computing, or some other classical methods, such as tensor networks or neural networks. But in this talk, I will just focus on quantum computing. So I want to show you a quantum algorithm to calculate the retarded Green's function for the shear viscosity calculation. This is the overview of the algorithm. So it has 4 parts. We will do a thermal state preparation, and then we will apply some operator for our commutator evaluation. And then we will do some real-time evolutions. And in the end, we will do measurements and analyze the measurement results so we can reconstruct the retarded Green's function. Okay, so let me explain this thermal state preparation first. And let us consider we have a system of NS qubits. And what we need to do is to introduce NS plus 1 ancilla qubits and couple them with the system qubits. So here in this plot, the first row is a system qubit, and the third row, a fifth row, and the seventh row. And the second row and the fourth row are ancilla qubits. And in this circuit, we need to apply a Hadamard gate and a CNOT gates, and then measure these ancilla qubits. What results we get from these measurements does not matter, But the important thing is after the measurement, the initial state, which is used to be all a pure state in zero, now becomes a maximally mixed state. So in terms of the density matrix, is written as an identity. It's proportional to an identity matrix. And this would correspond to an infinite high temperature thermal state. And what we need to do the next is to apply a so-called quantum imaginary time propagation circuit to cool down this maximally mixed state to the temperature of our interest. And this quantum imaginary time propagation is written in this way. So it's a kind of a block diagonal, it's a 2x2 block matrix. Each block has a dimension of 2 to the ns times 2 to the ns. And these operators involve the Hamiltonian of the system and also some parameters like a p and the et. So in practice, we just need to choose the p to be 1 and the et to be close to the ground state energy, and then this circuit will work. And after this quantum imaginary time propagation, we will measure this final ancilla qubit here. And if we measure this ancilla qubits to be 0, that would mean the state of this system is in the thermal state at the temperature we want, the beta. The beta is tuned by tuning the tau in this quantum imaginary time propagation here. And for example, we can choose tau to be beta over 2 to get the thermal state we want. Okay, and the next step is to kind of apply another operator for the commutator evaluation. So this is just a kind of simple exercise. For example, if we consider two operators, A and B, their commutator can be written in this way when A is a poly string, a string of poly operators. So this would involve two circuits. One circuit would have a plus I pi over 4 times A, and another circuit will have a minus sign here. So for example, if we want to evaluate the commutator in the retarded Green's function, we need a Txy commutates with each other. So in practice, we just take this Txy and treat it as this A operator here, and this Txy summed over all lattice point as the B operator. And what we have is just like on the lattice with our truncation, this Txy at the point ij can be written in terms of some Pauli matrices. And we call this Pauli matrix the sigma 0, and these Pauli matrices as the sigma 1. And then it's just like a combination of these two terms. And then we can apply this formula to each term here. For example, for Txy commutates with sigma alpha, we just infer this expression and get two expressions here. And since this Txy is evaluated at time t, we can just use the kind of Heisenberg time evolution to write the time dependence in this way. It just involves the time evolution driven by the Hamiltonian. So from these expressions, we just need to use 4 different quantum circuits to evaluate the commutator. So first, we need 2 different circuits for the 2 sigmas here. So one sigma will have these Pauli matrices, the other sigma will have these Pauli matrices. And we also need another 2 circuits for this difference, because one circuit will be involved with a plus sign here, and another circuit will be involved with a minus sign here. So this is another 2 circuit, and in total, we will have 4 different quantum circuits to evaluate retarded Green's function. And for the real-time evolution, we just do the standard tractorization. For example, the time evolution driven by the Hamiltonian can be written as a product of time evolutions at smaller time steps, delta t. And for each small time step evolution, we just decompose the time evolution operator in terms of the electric part of the Hamiltonian and the magnetic part of the Hamiltonian. And we know how to construct the quantum circuit for each term in the Hamiltonian. For example, for a 2x2 lattice with the Gmax equals 1/2, we can decompose the magnetic term at 1, 1 position in terms of this circuit here. It involves some Hartmann gate, Z rotation, and the C0 gates. And the final step in the quantum circuit is to do a measurements in the computational basis. The computational basis is just spin up and spin down, and they are labeled by the B states here. And we need to measure, upon all possible basis states. And luckily, this TXY operator is diagonal in this computational basis. So we can do an easy reconstruction from the measurement results. For example, if our measurement gives us a B basis state, then it will contribute to the final results in this way. So it will contribute as the diagonal part of the TXY matrix element. And then this is the kind of measurement probability we get from the circuit by repeating the circuit many, many times. The plus is for the circuit with a plus sign here in the pi/4 term. And the alpha labels whether we use the sigma 0 or sigma 1 terms. And in principle, we will have 4 terms for that, plus, minus, and the 2 different alphas. And then we just need to collect all the results and do this reconstruction to get our retarded Green's function here. Okay, so here are some systematics of this calculation. The first important thing is how much error would we get from the trotterization in both the real-time evolution and the quantum imaginary time evolution. And here is an analysis of the trotter error. And from this plot, you can see the trotter error associated with the imaginary time evolution is very small, but the trotter error associated with the real time is still reasonably large. So we need to use a very small real-time step in practical calculations. But for the imaginary time propagation, one step trotterization is good enough. And we also need to do this integration because once we get this retarded Green's function, we still need to integrate over time to get this eta tilde, and the shear viscosity is extracted when the eta tilde is evaluated at an infinitely large time. So that means our calculation would involve a numerical integration. And if we use, for example, the Riemann sum as a numerical procedure to evaluate the integral, we also need to be careful about the errors in the finite sum, because if we choose a large time step in our finite sum, we would get a large error from the Riemann sum. But that also gives us an advantage in the quantum calculation because we need to evaluate the retarded Green's function at each time step. And that means we need to time evolve to that final time and then do a measurement. And after the measurements, the wave function is totally collapsed. So we need to restart. So in other words, if we can kind of reduce the number of points we do these measurements, we can save a lot of quantum computational resources. So in practice, that will be a kind of play between the Riemann sum error and the number of quantum resources we need. So that's why we want to study this uncertainty here. And this plot just shows the finite Riemann sum difference from the exact result. As you can see, this error grows roughly in a cubic way. When we choose a time step to be 0.1, this error can be under good control. Okay, so finally, this is some quantum computing results on quantum simulators. So I use 2 different quantum simulators. The first one is called the Continuum simulator. The other one is the simulator provided by the IBM quantum machine. And we studied for a small lattice. This is a 2x2 lattice with the largest Hilbert space truncation, and we choose these parameters for the calculation. And you may see from this plot, we have a huge bar from these blue points here. And this huge error bar is coming from the very limited number of shots we have. So the number of shots is just the number of times you can repeat your quantum circuit and do the measurements to collect statistics. So the large error bar here is a statistical uncertainty. And the reason why we only get 500 shots here is because the Quantinuum hardware is a trapped ion system. They have all-to-all connectivities, which is very good, but to apply gates in their system takes a long time. And that's why, doing many gates and many shots on their hardware is very expensive. So they only give us 500 shots to do a demonstration to them to kind of show, you can use their hardware to do some useful things. But at the moment, obviously, with only 500 shots, we cannot do any calculation related to the shear viscosity. On the other hand, the IBM hardware, which is based on superconducting qubit, doing many shots and many gates is relatively cheaper. And in fact, we can easily do 1 million shots or tens millions of shots. And you can see from this plot, after we increase the number of shots to 10 millions, the error is much smaller in this plot. And this is the right plot is a zoom in of the first plot. As you can see here, like the error bars are relatively small compared to the continuum case. And we can also estimate the number of shots we need for a good accuracy. So the epsilon here is the accuracy we want to achieve our results. And by using the kind of largest magnitude of the GXY, we can estimate the number of shots we need in practical calculations. But another point I want to emphasize is besides the number of shots we need, we also need a lot of number of points along the time direction. So each time point here would take 10 million shots. But in practice, since we need to do an integration after these evaluations, we need this t to be at a much later time. For example, t equals 100. And that would require probably 1 billion number of shots in practical calculations. And at the moment, I think only the superconducting hardware would allow us to do that. Okay, so with that, I would like to conclude my talk. So I hope in this talk, I persuaded you that shear viscosity is a very interesting physical quantity to calculate, but very hard to calculate in QCD. And in this talk, I discussed the Hamiltonian approach for real-time calculations. And I show you basically two things. One is based on classical computing. We do exact diagonalization on a 4x4 lattice with a large Hilbert space truncation. And our model calculations shows a consistency with a 1/4 pi in the naive continuum limit. And we also see a peak structure in the spectral function when omega is small. And then I introduced a quantum algorithm to do this real-time calculation. And hopefully this will help us to take the physical limit in some time, maybe 5 or 10 years. And finally, I want to conclude that all the results I showed here have unknown systematic uncertainties because we're still far away from the physical limit. And the ultimate goal in the next 5 or 10 years is to really reach the continuum limit and pin down the shear viscosity for a non-Abelian gauge theory. Okay, with that, I would like to thank your attention and I can take some questions.
Thank you very much, Xiaojun. Thank you everyone for sticking around through the technical difficulties. And thank you for a very interesting talk. So unfortunately, Paul was not able to join us after all. Mm-hmm. So Stefan has very graciously offered to help chair the QA session. So I'll turn it over to Stefan. There was one question in the chat from earlier, and then I see a hand up also from Bern. So Stefan, please go ahead.
All right. Thank you all. Please use the raise hand mechanism so I can see who wants to ask questions. And for the question in the chat, Yao, could you reformulate that since it's not clear anymore to which slide you were referring to? And while you do that, I'll call up on the first person raising their hand, and that is Bernd.
Okay, so I assume that I'm on.
You are.
So Xiaojun, great talk, and very impressive first step in the direction of determining the quantity that everybody would like to have a quality result in the full lattice gauge theory, in the continuum limit for large lattices. I mean, to put into perspective what you said at the end in terms of the scaling with the number of shots and the gates and so forth.
Yeah,
I think it's useful to recall that if you try to do this calculation in some of the rudimentary forms on a digital computer using a Euclidean lattice and then analytically continuing, I think what you need is approximately 10 to the 20 or so floating point operations. I could be off the mark here by 1 or 2 orders of magnitude, but we're talking about at least several petaflops and many, many, many seconds of computing time. So we're far, far, far away from that now, what can be done on current quantum computers. Of course, if you go back 50 years or 70 years, what could be done on a digital computer was probably comparable to what can be done now on a quantum simulator or some other quantum computer. But it took 70 years to get here in terms of just the hardware evolution. And so my question is whether you or anyone else has thought about how long the path actually will be to do a realistic competitive calculation of a quantity like the shear viscosity on a quantum system. Is it also about 70 years, or are we talking about more like 10? That's a big difference for people with a lifetime of, in that range.
Yeah, that's a very good question. Yeah, I don't have the ability to predict the future precisely, but I can see a few thoughts I have. Like if we sit through some quantum computing talks, especially the hardware talks, they always show a roadmap towards the future. And one kind of amazing plot is from the IBM. They show a roadmap plot starting from 2020, I think. And they already listed their goals in 2020, and they are very good at achieving their kind of goals during the last few years. So what they promised back in 2020 was already achieved now, and they very stick to their plan. So in some sense, if we believe the IBM roadmap, then I would say by the time of 2030, which is in 5-6 years, these quantum hardwares would allow us to do a more kind of a calculation that is closer to the continuum limit. They would have a few hundred, say 500 qubits, and they're robust against errors, and one can do the number of gates on the order of 1 million gates in the circuit.
Okay, thanks.
All right. Yao, you had a question earlier.
Yes, I will just reformulate over here. So Xiaojun, thanks for the great talk. So it's for the question when you talk about the matching from eta, basically the green Kubo-formula you showed at some earlier slides. Yeah. So can you elaborate more on what you worry about this tree-level matching? Is that so for eta is indeed some quantities we just decompose the energy momentum tensor, and then we call some coefficients in the gradient expansion eta. While on the right-hand side is some fully quantum computations. So when I do the matching, is this matching still exact if I just go to the thermodynamic limit where you can, to first approximations, neglect all the fluctuations, or there's some intrinsically like terms we need to consider order by order that this formula it need to be corrected.
Yeah, I would say there's a order that we need to systematically include. For example, like when we expand the stress engine tensor in terms of the gradients, we usually keep to the kind of linear terms there. But if you start to include the nonlinear terms into the T mu nu, then you would have a term that contributes as a loop to the retarded Green function. And in that case, you would have eta time eta plus loop integral times eta, something like that. And that loop integral will give you a divergence, and that divergence in the end is translated to the scale dependence of the eta.
Okay. Thank you.
Sure. Yiyan had a question.
And actually, I have a related question because, in fact, I think 10 years ago, the Paul Romashkin, and who's supposed to be the chairman of this section, wrote the paper with, I think, Guy Moore. I think he computed the so-called loop correction. So for these cases, I think in 3+1, the correction to the eta is like a square root of omega in 3+1D. But I think in the 2+1, the correction is logarithmic omega. So it's not only UV divergent, but also IR divergent. So do you need to worry about that?
No, I think in the end of the calculation gives you a log mu, where the mu is the cutoff of the hydrodynamic theory. Yeah, so I don't see an IR problem here. The mu is coming from the cutoff of the hydrodynamic theory.
Maybe we can discuss later, but I think I remember is for the 2+1 is very special because the lower the dimension is, the larger the fluctuation, IR fluctuation is. But maybe I can send you the reference later. I think it's the paper by Romashkin and Gamore. But can I ask you a question actually on the page 18?
Okay. Oh, this is the 50.
The plot of rho.
Oh,
which,
yeah.
Sorry, yeah, I just want to be sure. Can you just elaborate more which one is? I see the blue one is the weak coupling and the red one is the additivity. But do you have where is your results?
Oh, my results is on the left. Yeah, this is a known results. Like if you look at this expression, rho xy divided by omega is just get rid of this omega, and then you have the rest of terms. And then basically, the omega dependence is determined by this matrix element squared. But in this plot, I just plot this matrix element, and you sum over all the state. It's just like taking an average over all the matrix element. At on the individual matrix element level, we already see a peak structure here. And if we sum over all the states, then it will collapse to a line, and that line will have a peak at small omega.
Yes. And can I just ask? So, if I look at your result here, it seems your peak looks very broad. Is my understanding correct?
So that,
maybe it's hard
no,
to tell.
Okay. Okay, if you want to compare with the right plot, then one needs to do a proper scale fixing. So yeah, so here this has no temperature here. If we want to do kind of more accurately, we need to plug in a temperature, include this factor in the summation, and then compare this x-axis with the temperature we used in this vector. But I would see this peak goes way to 0.2 here, and here is also 0.2. So it's not that broad, in my opinion.
I see. Just out of curiosity, can you also compute, say, the sound velocity from your method? How good it looks like?
Yeah, we're right now looking at the kind of extracting the sound mode and also the diffusing mode from this small lattice. Yeah, it's ongoing, and
Okay.
I can let you know once we have something.
Daniel,
Okay, thank you.
Daniel.
Yes. So thank you again. I think I know you can't predict the future, but kind of going back to similar to what Bernd asked. If, for instance, if you took the quantum computing, the hardware side out of the picture, so tomorrow I just gave you a quantum computer that worked with plenty of gates. What are the main other challenges in this approach and the other aspects that would need time to be developed?
Okay. Good. Yeah, I mean, all the real-time part, the retarded Green's function, they're all working okay. But the one challenge is really the thermal state preparation. So let me show you that. So the thermal state preparation requires us to measure an ancilla qubit, and we need to get a measurement result 0 to be successful in the thermal state preparation. Otherwise, we need to restart. So that means we need to, repeat the circuits many, many times before we successfully prepare the thermal state. And the success probability can be calculated in this way, where E0 is just a ground state energy. And here in this plot, we show the success probability at several temperatures. As you can see from this plot, the success probability decays exponentially with the system size. So if we have a very, very large volume, the success probability is probably very small, and we need to repeat the quantum circuit for the thermal state preparation many, many times before we reach a good thermal state. But on the other hand, when the beta is small, which means at high temperature, this is exponential with a very small prefactor. So it's not that bad, even though it's exponential, but it's not that bad, maybe for our kind of interest. And I want to kind of argue in this way because the global mass, which is really the first excited state energy in our system, is 6.2 in lattice units for this lattice setup. And if we take the inverse of that, this is roughly like 0.16. So something definitely kind of better than the green curve. And that would be what we call high temperature, right? For example, in QCD, the crossover temperature is about 150 MeV, and the pion mass is 140 MeV. So for our interest, we only need to prepare a thermal state at a high temperature. And in practice, that high temperature may only correspond to exponential, cost with a small prefactor. So maybe not that bad. But yes, the thermal state preparation will be a challenge, and or could be a challenge, and we should put more kind of thought or algorithm development for the thermal state preparation.
And just from my understanding, so this is totally separate from the actual quantum computing hardware. Is that right?
Yes. This is an algorithm level.
For setting up the ancillary bits, as you said.
For getting the thermal state in the
Okay.
first step, right? This part.
Okay. Thank you.
Sure.
All right. I see no more questions from the audience. So let's thank Xiaojun again for this great presentation. And I guess we are adjourned for the day, unless there are any other announcements.
Yes, I'll just say thank you again to Steffen for stepping up at the last moment. And I'll be sending another announcement soon for our seminar in 2 weeks. So I hope to see all of you there, and have a good week. Bye, everyone.
Thank you all. Bye-bye.
Thank you. Bye.